Hi, welcome to the BYU-Idaho Tutoring Center video. Today we're going to be talking about energy and the role they kind of play in ecosystems and how they flow through ecosystems. So to start off, we're going to look at primary production. So primary production is just the amount of light energy that is converted to chemical energy by autotrophs in a certain ecosystem over a certain period of time. So basically we're just looking at how much of the light energy that's coming in are we able to change into the chemical energy. And this is important because this kind of sets up our overall budget for the rest of the ecosystem. Because however much chemical energy we're able to make by these autotrophs is thus going to be the energy that we're going to be able to transfer to the rest of our consumers and support in our ecosystem. And so two key definitions that you're going to want to be able to understand is gross primary production, which is abbreviated with the GPP, and this is just the total production that we have. So kind of going back to this definition, just how much of the light energy that eventually is being changed to chemical energy. Whereas net primary production, NPP, looks at how much gross primary production we have minus R, and R just stands for the energy used for respiration by the autotroph. So some sort of plant might be making and storing light energy or changing it to chemical energy, but it's still going to have to use some energy that it makes, so those sugars, for its own cellular respiration and to support its own life. So not all of it's going to be stored to be used by consumers. Some of it has to be used for itself. So that's the one we kind of care about more when we're looking at this, is net primary production, because that's going to tell us how much we have available for the consumers. And so when we look at the amount of primary production that we have in a certain ecosystem, ecologists like to try to understand what could be limiting that, because that can be impactful for a variety of different applications if we want to have more primary production or if we want to reduce primary production because of the effect it may be having on the ecosystem. So we kind of distinguish between some of the limiting factors for aquatic versus terrestrial ecosystems. So in aquatic ecosystems, one really important factor is light. We know that light is important because that's our ultimate energy source, or the energy that we're converting from light to chemicals. So if we don't have that light, we can't do photosynthesis. And we know that in aquatic biomes, as you get lower or deeper and deeper into the water, we have less light that's able to penetrate. So one thing that we look at is the amount of light that's penetrating into the water. And so we kind of find that as you go deeper into deeper water, we kind of have some less of this primary production because there's less light that's reaching there. However, if light was the only limiting factor, then we'd expect to see this overall trend, which is you get closer to the surface of the water, we have more primary production, and so then it would be kind of the same across all levels. But that's not the case when we do observations and tests. We find that it's still different as we get higher, and so there's got to be something else that's limiting our primary production. And so that's where nutrients comes in. Nutrients can also be a limiting factor, and we call it the limiting nutrient, or the thing that if we added it to our ecosystems, we would be able to increase our primary production. And when we look at aquatic ecosystems, a lot of times that's nitrogen and phosphorus. And so scientists will do experiments in which they will add nutrients that they think might be the limiting nutrients into the environment, and they'll see if primary production increases. And if primary production increases when we add that nutrients, then we can say, that was limiting nutrients. And so as far as a test or a quiz goes, you're probably going to be asked to look at some graphs or some charts and interpret them and try to determine what the limiting nutrients is. And so, for example, if you were given some sort of graph like this, and they indicated the different nutrients that they put in at different sites and the different change in the overall either primary production or the number of organisms that could do that primary production, because a lot of times that's what we're looking at. If we increase the number of plants or photosynthetic prokaryotes, then we can assume that we're going to be increasing primary production. So in this case, we have our nutrients 1, our nutrients 2, and then the black represents we didn't add any nutrients, so that would be like our control. And we see that we have the most primary production, or the most organisms, when we had nutrients 1. So we interpret that nutrients 1 is the limiting reactant. The same thing could happen with a chart, and it could list the nutrients that we added, and then some measurement of primary production. So in this case, we have one in which we didn't add any nutrients, one in which we added nitrogen and phosphorus, one in which we added nitrogen, phosphorus, and metals, but the metals did not include iron, one in which we added nitrogen, phosphorus, and metals that did include iron, and one in which we added just nitrogen, phosphorus, and iron. And we see in the ones in which we had iron, we had a lot more primary production than the ones that did not contain iron. So we would guess that our limiting nutrient was iron. And so just be able to interpret these graphs, it doesn't require a lot of knowledge as far as it goes in ecology. Mostly you just have to be able to use common sense to interpret a graph. And then when we talk about terrestrial ecosystems, some things that we mostly focus on as limiting factors are temperature and moisture. This kind of explains why around the equator we have the most primary production, is because we have a lot of moisture and warm temperatures. And this kind of all goes back to this idea of evapotranspiration. We found that in areas that have more evapotranspiration, we tend to have more primary production. And evapotranspiration is, remember, based on both evaporation and transpiration. And so if we have more moisture, then we can have more of this transpiration, and if we have more heat, then we can have more evaporation. And so that's the trend that we see. So now we're going to move on to production efficiency. And so first we have to look at this idea of secondary production. So secondary production is the amount of energy that a consumer intakes from a plant that it now is able to create into new biomass. So it's kind of going back to this maybe idea of primary production. So when we were looking at net primary production, we took the total primary production minus the respiration. So when we do secondary production, we'll take the amount of net primary production that we got from the plant, however much energy the animal ate, and we'll see how much of that is made into new biomass, so like for growth or reproduction, and how much it was used for cellular respiration to just keep the organism alive. And then that will allow us to see, okay, how much of that biomass is now available for a next consumer to intake. And so production efficiency is just the percent of energy stored in an assimilated organism over the amount of food that isn't used for respiration. So we kind of just look at this percent, how much of the energy that they intook from the plant is going to be available for another thing to intake, and how much is just used for cellular respiration. And so we find this kind of overall trend. It's kind of our 10% rule, that about 10% of the energy stored in one organism is then available for an organism at a higher trophic level. So this is where we look at the trophic efficiency. So for example, if there was only 10% of the energy that was available in this primary producer is going to transfer up to this primary consumer. And only 10% of that energy is going to transfer up to the secondary consumer, and only 10% is going to transfer up to the tertiary consumer. So that's why we can't have these super long food chains, is because eventually if we kept going up on consumer levels, they would almost have no energy that they could consume and support themselves. So, because if you think about it, only 1% of the energy in the primary producers is going to the secondary consumers, and only 0.1% of the energy from the primary producers is going to the tertiary consumers. So we kind of see these pyramids like this. However, we have to be careful when we're looking at kind of the biomass versus the production. So remember, biomass is kind of how much of there is available at any given moment. And so we see this different trend when we're looking at aquatic biomass pyramids versus terrestrial ones. So this is an example of kind of the beginning of an aquatic biomass pyramid, and it's what we call it an inverted pyramid. So we have our primary producers having a lower biomass than our primary consumers. So if this is our phytoplankton, this is our zooplankton. And so the reason for this is that our phytoplankton are being intaken faster almost than they could replace themselves. So we have a lot of phytoplankton being made, but they're being consumed by the zooplankton so fast that it doesn't look like we have a lot of phytoplankton. And so if you were to actually look at the amount of biomass versus the amount of production, we'd see that the amount of production that's going on with the phytoplankton would be it would be bottom heavy like this case. But when we're looking at the biomass term, which is actually there in the environment at a given time, there's more zooplankton than phytoplankton biomass. And so this just has to go back to the idea of turnover time, of how fast the phytoplankton is getting consumed versus being produced. And so just the last final thing I want to touch on is kind of an application of this tropic efficiency. As we've had an increase in our population size, one potential problem that we've looked at is being able to feed everybody. And so because we know that it's more efficient, or we get more energy from consuming plants than from consuming animals, it's this idea that we should, as a human population, be focused on eating more plant products, not animal products, plant products, because it's more efficient for this transfer of energy, and we'd be able to support more people than if we're all trying to eat meat. So that's going to be all for today. I hope this video was helpful. The main things that you're going to want to focus on studying for a test or a quiz or a homework assignment is going to be the distinction between gross primer production and net primer production, being able to interpret these types of graphs to figure out what the limiting reactant is, and just knowing this idea of the 10% rule, that we only have 10% go to the next level, but also be aware of this inverted type pyramid, biomass pyramid. That's going to be all for today. Thank you so much for watching, and have a fantastic day.